welcome back. Well, welcome back to me, I guess. We are continuing with our custom marching cubes script rework. And today is going to be the last tutorial or last lecture of this kind of mini series. So let's pick up from where we ended last time. And I believe last time we did this element right here, element number 5, right? So I'm not going to continue modeling. I already did that for all of the elements because I think you know the idea by now, you know how it works. And also I kind of need to fix the camera. Yeah, should be better. So you know how it's done, right? You know how it's modeled. So I'm just going to really quickly go through the remaining elements and just show you what we're going to be working with, right? So element type 6, how do we do this? Let's do it this way. The starting geometry for element type 6 was this, and this is what I came up with. You know, nothing too fancy. The backside is pretty cool though. I like the backside. Then element type 7 was like so. And I just kind of connected all of the triangles with different bridges, right? Just messed around with that. Element type 12, well, there was a triangle here and hexagon. Is that a hexagon? Yeah, that's a hexagon. A hexagon here. So I just kind of bridged them, created a tunnel, and then added a little bit of detailing to the tunnel to come up with this shape. All right. Element type 13. Wait a minute. No, I messed up. I immediately jumped from element 7 to element 12. Element 8 looks like that, really simple. Element type 9 and element type 14, both of them are basically the same element, only that it's mirrored. So I wanted to keep it as simple as possible. And this is what I came up with. Basically just a single hole in a, other than that, a pretty solid surface, right? Then let's go backwards. Element type 13. This was a pretty interesting one. Just two rectangles, and what the hell do we do with those two rectangles? So what I ended up doing was taking element type 2, right? Copying it, and then bridging the gap between two copies of element type 2 to get this kind of form. Already talked about element type 12, element type 11. This is my favorite. This is by far my favorite element. It's basically a triangle and a rectangle, right? That are joined together. But the surface qualities of this one is, I don't know. I really like it. And I spend a lot of time on it with, you know, different topology operations. I think it kind of shows. So element 11 is my favorite. And then we have element type 10, which is basically like two triangles being connected by this kind of framework ribbon cable thing. Right, so we have our 14 elements, well, 13, because as per usual, element type 0 is empty. And we're going to actually grow a structure from them, and that's going to be our tutorial for today. And for this tutorial, I am going to do something completely different and something that I usually only do with my students in the university. And I'm just going to test it out and see if this works on YouTube as well. So instead of this kind of let's just follow along the teacher and just blindly copy what teacher is doing to build up your own script, I will try to explain the logic of the script to you and the logic of what has been changed with the script, right? So instead of just giving you like step-by-step tutorial on how to get to the end result, I'm going to explain my thinking process of how I'm creating it. Said that, this definition as well as the 3D models, the elements, are going to be available for the Patreon supporters. Yay, as per usual. So if you want to just kind of skip ahead and don't care about me explaining things and just get the definition, you can do so, but that's gonna cost you money. Just support the channel, right? Anyway, I already, like, this definition that you currently see on the screen is, most of it, like 99% of it, has been already made by me in a previous video, and I'm going to put a link to that video in the description of this video, right? So the link is below, right? So we have already built this in a traditional sense, like with a traditional tutorial. So here in this video, I'm just going to explain what exactly am I changing and what exactly what's my thought process for changing things, right? So before we do that, I guess I first need to explain the logic behind how this whole thing worked before, right? We basically had a cloud of points with gaps, with kind of constant gaps of, what's the voxel size? Constant gaps of 10 centimeters, right? So if I were to just kind of draw the point cloud real fast, let's say one point was here, and then I can only copy it by 10 centimeters to the left, to the right, or upwards, right? So let's say 10, then upwards by 10, something like that, and then let's say to the right by 10, right? So the points were always anchored in the point cloud, were always anchored on the corners of the voxels. That's very important. You know, the step size is very important, right? So constant step size of 10. Doesn't matter if it's millimeters or meters, but what matters is that your voxels in which you model out need to be the same size, right? And then we would use this kind of marching cubes algorithm to generate a structure around these points. And that algorithm would basically get all of the possible permutations of these voxels. And by permutations, I mean like this element right here can be also placed right here, like so. It can also be placed, right here, like so, and so on, right? So, for instance, element type 1, since it can be anchored to any one of these corner points, has 8 permutations in total, right? 8 ways of how it can be placed inside of the voxel, depending on which point does this voxel, which point of this voxel is alive, let's say, which corner point. And then the same thing for element type 2, element type 3, and so on. So all of these elements have different amounts of permutations, and that is what we have done in this cluster right here. We created a crap ton of permutations, right? And I can kind of show you this. I don't really want to, but let's say set one geometry. Let me just set this point. And I believe now if I enable the preview of this, yeah, you can see all of the different permutations of this. Again, all of this I have already explained through and through in my previous tutorials, right? So if you're interested to kind of look at what's inside of that cluster, just check out that link right there, right? So all of the permutations are here. And I'm going to just clear values right here, just so that it's not in our way for now, so that it's not laggy. And then so then we would take all these points, right? This point cloud, and we would, let me stop the definition, probably there. Yeah. Set multiple points, there we go. We would take these points and we would create a voxel, let's say, space, voxelized space around them, right? Surrounding them. And then each voxel, let me actually bake this out so that you can see better what I mean. Let's bake it out like so. Disable preview of that. Get this into the ghosted preview state. And let me actually, maybe ghosted is a bad idea. I'm just trying to figure out what's the best way of how to show you the behavior of the voxels. Let me just leave one box, right? Just keep in mind that we have like a bunch of boxes here, but let me just leave one box, right? This one right here. So this is a voxel, right? And this voxel gets a corner point, the top, top right far corner point. That is where a point is on this voxel, right? So then the script, what the script does, it basically goes through these and asks which one of these permutations, so these are just initial states, right? Permutations is a much, much larger list. Which of these permutations fits with, this exact state, right? And of course, the permutation which will fit is going to be from element type 1, where this point is located right here, thus the element is flipped to that side, right? And then once it recognizes that, it takes that permutation and it moves it to this place. Okay, there's a lot of kind of mumbo jumbo going on, I understand, but that's the basic principle of it. It checks every voxel and it chooses the correct element, right? And it does so by getting like true and false statements for every corner point, right? So that's how it worked, how it used to work, right? Now, or actually, let me just show you. Just a second. We have 27 boxes, so we'll need to run the loop 27 times. Reset. So it goes through every voxel and it records what kind of element needs to be in that voxel. And then if I press the reset button here for bake, bam, we have a structure. Easy, right? And that first element, the element about which I was talking about, this element, right? That's exactly element type 1, right? Just as I said, right? So it creates a structure. Now, when I have your attention, we can continue. We will make this really cool, I promise. All right, so that is the initial concept, right? So now what has been changed from there? I have marked out in green stuff that I have changed. And first I will just talk about the logic, right? So the biggest issue with the custom marching cubes algorithm before was that it was super slow, right? If you needed to populate 200 voxels with meshes, with elements, it would become really, really slow, really, really fast. Really slow, really fast, what? But it makes sense, right? Your computer would have a hard time. So I decided to optimize it. And the best way to optimize these kind of structures is by saying that, instead of just copying the geometry over and over again, why don't we just create a block for every geometry, right? And that is exactly what we're doing here. Define block. What's it called? Bifocals, right? And then let's try doing it this way. Draw icons. There you go. Define block. This little node right here is comes from a human plugin. Human as a person. Human plugin. You just download the human plugin from Food for Rhino, or I believe it's even in Package Manager. If you type in Package Manager here and you just search for human, yeah, Package Manager, human, and you can just install it. Or if you can't find it over Rhino, then just you can find it over foodforrhino.com. At foodforrhino.com. My English, yikes. And the way define block works is basically it asks you to give it geometry and to name that geometry, to give a name for that geometry, right? So the geometry that I am referencing here is basically every element, right? Let me just clear that just to show you how I do it. So geometry that I'm referencing here is basically set multiple geometries, bam, 1, 2, 3, 4, and so on, right? Notice how I am going from the smallest number to the highest. I'm not picking randomly. I am going 1, 2, 3, 4, 5, 6, blah, 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 right? That's because we want the naming of these elements to be correct. That's important, right? So now we wait. Now it gets referenced, right? And then basically here the idea is that I need to give each of these guys a name. So I put them with graph, I put them in separate tree branches, and then I just say, okay, I will have an EL, like element, at the start of the name for each block, and then I will add a number, right? And I'll add a number according to how many elements I have, right? So in total I have 14 elements. So I just go, okay, wait. That's weird. Why am I doing that? I am counting from 4 until 14 and then merging here. Oh, sorry, yeah. So now I need 14 ELs, 14 of these letters, EL, right? So I can do that by repeating data. By using repeat data, I just get 14 of them. And also I need 14 numbers like 01, 02, 03, blah, blah, blah. So I get that by using series, right? Starts at 1, ends at 14. Here I just chose for it to not start at 0, but rather start at 1. Then I merge these, and now you can see EL13, EL14, and so on. And then I use text join to join them up, right? And thus I have, a name for each of these blocks, right? Very important. So the blocks are created in Rhino, not in Grasshopper. That's an important thought to have. And I can kind of show you by typing in block manager. And you can see that, these blocks are already created. So that those 3 seconds were for creating the blocks, right? So these blocks already exist in Rhino, and from here on out, I can fetch them with the same human plugin. I can fetch them anytime I want. Great. Blocks do not copy data. Blocks reference data, meaning that every time when I create a copy of a block, my file size doesn't increase, and the computer doesn't need to kind of worry about my my whole file bloating, right? So that's done. Okay, we have defined 14 blocks, easy. Next up, instead of, before we used to just take a mesh and copy it, right? So now we're going to be doing the same thing, only that we're going to be copying blocks. And you can't really copy blocks. You can just place blocks, right? And I will go a little bit backwards on this. And I'll show you the last node right here, place block. And I guess this node should also be colored green. Place block, which basically asks us for, well, honestly, two things, let's say three things. Two things are important. This one is just a button that will bake out the blocks. So it asks us for names of the blocks, and it asks us for transformation of the blocks, right? How do we transform the blocks? So, okay. If we get a transformation value, transformation means movement plus rotation plus mirroring, right? All three of these are different ways of how you can transform things. So if we take a block, let's say this guy right here, and we record how it was rotated to fit to the correct, point of the voxel, right? So in our case, it's kind of oriented here. The element type 1 is oriented here. So how is it oriented? If we record that, and also if we record where does it get moved, then we have this kind of transform, which we can then say element type 1 should be in total transformed like so, to be oriented correctly and placed right here, right? So let me give this as an example. I will just repeat this. I will not repeat this. I will do this 0 times, right? So we are at the first voxel, and as I mentioned before, first voxel gets element type 1, right? And it rotates it to here. Thus, the name should be element 1, right? And I can kind of check what comes in through the wire here. Okay, that's compound transformation. I'm stupid. That's the name, element 1. And then transformation is carried out. Well, I will talk about transformation in just a second. The more important part is that it does choose the correct element, right? Element type 1, and it moves it here. I'll click the big button and voila, we have ourselves element 1 baked here. And if I select it, it says 1 block instance selected. Perfect. Okay. So that is done. Now we are going to, go backwards, I guess. Names are kind of simple to record. I will talk about names first and then about transformations later. Names are kind of simple to record here. That has to do with this node right here, or series of these series of nodes right here. So according to the rules, right, that we get, in this case, it checks every corner, and it says every corner of the voxel, of this voxel in particular, and it says which corners have points in them, right? So it has only this set to be true. And this cluster, since it has rules coming out, right? I call these rules, and I can kind of show you. So 1 is true, 0 is false, right? Since this cluster has rules coming out, all of these clusters do, it will kind of go through the rules and see which ones fit, right? If I were to grab a number, create a panel, you can see that we can easily convert false and true statements to numbers, right? So now it goes through all of these rules and it goes like, hey, wait, this one seems familiar, right? This and this, these two are identical. And then bam, it will immediately get permutation number 6 from element type 1. And it will say this one fits, I will be using this one, right? For instance, element type 2 uses 2 points. Thus, all of the rules for element type 2 will have 2 number 1s on it, right? That's an important distinction, right? So it basically, in doing so, it chooses the correct one, and this cluster does that. So what this cluster used to parse through, and maybe let's not talk about it too much. Yeah, let's not talk about it too much. But before, basically, this portion of the script used to parse the geometry, right? Because we were constantly copying the element and we were then pushing through an element. In this case, we are not pushing through an element, but rather we're only pushing through a compound transformation. We are just saying how that element should be rotated. Very important, right? So that instead of just getting the permutation and moving it, we are just transferring information on how the element should have been rotated to get to that permutation, right? Really saves a lot of time. So once this is done, and I can kind of show you the cluster again, just so that if you want to copy it, just pause the video here so that you can see. There we go. So once that is done, the transformations, not just the transformation, sorry, a group of things, so it's like two results, will come into the entwine and will be spit out through the output of the entwine, of course, right? So here we have 2 things coming in. Compound transformation, that is basically information on how that element was rotated, and then referenced point. The referenced point is, I believe, yeah, it's just straight up this little point right here, right? And for every element, it's going to be the same reference point. If I am not mistaken, I shouldn't be mistaken. Data reference point. Sorry, I need to double check. Teacher is confused. Please hold. Element 1. Element 1 is type 2. And then here we also get a referenced point, and it's the same point. Okay, sure. Yeah. So that works. So it is indeed always bottom right corner point. Always. Right? A point that has the smallest value for x and y and z, right? So it's always to the left and to the bottom, let's say it like that. Because why I'm using that point, that's because every time when you construct a box, that is going to be the first point of a box. Just convenient to do it this way. Okay. And as you can see, when I go through the loop and repeat it once, then we are at this voxel, and it finds, and it says that, oh, this is element type 2. And it indeed is, because element type 2 uses 2 points, right? And it's this one right here. And now if I press the bake button, you can see that element type 1 and element type 2 are baked in. So this just shows that the definition actually works. Okay, we can continue. So now, since we are pushing through a point and the compound transformation, it's going to arrive here, and you can see that the data tree is going to look like so. Most of the, not most, all of the branches are going to be empty, except branch number 2. Well, its address is 0, 1, but we're counting from 0, 0, so it's actually branch number 2, which is element number 2, right? So what we get is, how do we then read which element came through? Well, because we need the name of the element, right? Well, we can get the tree statistics, and we can measure the length of each branch, right? And it's basically just gives us, most of the branches are 0 except for this branch right here. And then with that, we can count from 0, 14 times. So this is 14, this is 0. So we can count from 0 until 14, right? And then by using the equality and asking if it's equal to 0, if the list length is equal to 0, we can call out the numbers that are not being used. Like that. And thus we get number 1, right? Again, we're counting from 0, so it's instead of element 2, we get number 1, that's fine, right? So now by using that, by using that number, we can use list item, and we can get all of the names of all of the blocks that were created right here. These are the names. And we can just use straight up use, we can flatten them out and use list item to get the correct element name. And then we just kind of feed it into the merge. This is a way of how I like to record a loop. Let me just show you in a separate example. Loop start. And this is an advanced tutorial or lecture, but I still want to explain simple things. 100. So you can record by choosing to record data right here, but I find it not to be fast. This is faster. If we merge like so, right? So let's say we start with a dog. Right? And then we add a cat. To the list of dogs, right? And we just need to flatten this out just in case. And let's just look at the output right here. Reset. You can see that, well, maybe this is not that clear of an example. Let's do with 2 repetitions. First, it takes a dog and it comes through here, right? And then a cat gets merged into the list of dogs, right? And thus you get dog cat. Then it gets fed into D0, goes through the list again, comes out here as dog cat. Then cat gets added again, so you get dog cat cat, and then goes through the loop again and adds one more cat, right? So we get dog cat cat. So if I keep repeating, we keep adding the cat, right? So this is a way of how I can, for every loop, if this changes, for every loop I can record what the output is, right? And I'm showing it to you with a finger, pointing a finger at the screen. I guess that doesn't work now, does it? So here, where you see merge, it's basically the whole group of names of the elements. I keep adding to that group of names the newest element, and in this case it's element type 2, right? And if I am correct, our first element was element type 1, right? So through this wire, there should be element type 1 coming in. So it's element type 1, element type 2. So the output of it is going to be element 1 and 2, right? Great. We are recording our list of names. Excellent. So now, at least for every voxel, as it's going through, let me increase this to 10. For every voxel, as it's going through this whole voxelized space, remember the voxelized space right here, this one? It is recording the names of the voxels that it's actually, or sorry, not voxels, names of elements that it's actually using, right? So it keeps recording and it keeps adding to that recorded list. Great, that's our first output. Our second output needs to be, how the hell are those elements transformed, right? So thankfully, I am pushing through the transformation of all of these, of the successful, let's call it successful permutation. I am pushing through that, through this cluster, already talked about that. So it comes out here, right? Comes out right here as compound transformation, right? So then I clean up the tree. So basically I just remove everything that, every branch that I don't need. And I'm left with this compound transformation and reference point, you know, a clean tree. Well, not a tree at this point, it's just a list, right? And then I just get the first item of the list, the transformation. I only care about that, right? So that transformation is going to kind of go all the way through here. And I will need to, so with this transformation, compound transformation, I know how it was rotated to get to the correct orientation, but it's still not moved. I don't add the movement. So I need to do that. And how do I do that? Well, by saying, you can already see the arrow, right? By saying, from the list of points right here, right? From the list of points right here that we have in the bottom left, choose the correct one by using list item and using the same call pattern as what we used for the name of the element, right? So it's going to just get me the correct bottom left point, right? So with that list item, I get the starting point from where the element should be moved. And then with, there we go, box corners. How do I explain this? Remember when I said that every box that is automatically generated in Rhino, or sorry, in Grasshopper, every bounding box is going to have its first point, its first corner point always at the bottom left, right? Its first corner point will always have the lowest values for X, Y, and Z. That is why we're using these points right here, right, as our starting points. And that is why in our voxel, in our current voxel with which we're working, if we deconstruct it and we just get the corner A, the first corner of that voxel, and we kind of just drag out this long wire up until here, that's the same corner point, that's always going to be the bottom left corner point. Always, right? So that's very convenient for us. And thus, then I just get, you know, bottom left corner point here, vector between 2 points, which you can actually, I am displaying it. You can see it here. It creates a vector and it just moves. What does it move? It moves nothing. We don't care. We don't need to move anything. All we care about is getting that vector, adding it to as our translation vector, and then getting the transformation. just the transformation information. We don't actually care about moving any geometry, right? So that's why these two are empty. And then what do we do? Well, this compound transformation that I was talking about, that's only rotations, right? And this is movement. So we just merge them. We first rotate, then we move, right? And thus we get compound transformation, like 3 rotations plus 1 movement. We use compound node right here, right? So we get 4 transformations in total. And for some reason here, wait, list length equals 2, equal number to compare to. If it's 0, then it should be called. I believe I have added this part. I believe this part was added just to fix a small bug where it would create a necessary branch, a necessary data branch. So this gets rid of that. I will not get too deep into this portion, but you can always copy it. Okay, so we have that going, right? And then what do? Well, we do the same thing as we did with the names. We just get the compound transformations like the previous compound transformations, right? We keep adding to that list with every loop, and thus we are saving a new transformation list, right? So almost done, almost there. So by the end of it, we get a list of names right here. We get a list of transformations that correspond to the names. You can see from 0 to 7, from 0 to 7, right? And then all we just need to do is click that bake button. And and also we actually need to properly run the loop, for it to do its magic. And to do that, I will just see 27 boxes in total, so 26 times. So I'm just running the loop, repeating the loop 26 times. Then I bake, and I get my little structure right here. Cell block instance. Move it to the side. Beautiful, beautiful. And let me just place it in the sub-D stuff layer. Cool. Hope this is cool. Wow. Okay, wanna break it? Let's break it. Right. So here, this is where I'm going to kind of start going weird about it, right? We could kind of write a script for kind of creating complexity, and maybe I will. So what if for these points we kind of generate random point cloud, right? And for this particular tutorial or lecture, I will be working with random points, a random point cloud, but I really encourage you to play around with different patterns, and I'll probably do a lecture on different patterns and how those interact later down the line. But for now, random is fine, just to kind of show you the principles of things. So I'm just going to probably create a construct point. I'll just construct a single point at 0, 0, 0. I'll just move it according to x direction, along x direction, by series of points. So the step size is always going to be 10, right? Because that's the step size of my voxel, right? And the count, I kind of want to control it. So for now, let's do 15. That's going to be our count, 15 points in a line, right? And then I'm kind of lazy, so maybe we should, yeah, we should probably do this. I'll just copy the movement and do it again. And instead here, I'm going to be using unit Y, like that. And you can see that now it's interpolating, so I'm just going to graft the output. Oh, that's not graph, that's flatten. I'm gonna graph the output of first movement so that we get a grid, right? So now it takes every point separately and moves it by series in Y direction. And I'm gonna kind of do the same thing to move it in Z direction. Just like that. Oh yeah, need to graft it again. Move it in the Z direction, right? So you get like this point cloud. There are different ways of how you can do it. This is the most manual one, I guess, but it works, right? If it works, it works. We will not be messing around with this slider at all. We will be messing around with these sliders, right? So let's say I want to create a pretty thin wall. Let's just say 4 points deep, 15 by 9, right? Something like that. And just to make it a little bit more interesting, because this is not interesting at all, I will flatten everything out. Flatten. And random reduce. Random reduce. I'll use that. That's our list, and it asks for number of items to remove. Okay, so we can do, let's say if we measure the list length of how many points we have in total, and we multiply it by 0.5 and add that, then it's going to remove half of the points, right? So now I can control how many points are being removed. So I'm gonna kind of use something like that, maybe, just, you know, as a test, and I'm gonna plug it into my point input right here. Okay, so that is done. Now I will just measure how many boxes I have. I have 800 boxes in total. And maybe we can just kind of automate this list length, because I'm kind of tired of changing the slider here. So just measuring the list length, subtracting -1, subtracting 1 from it. Don't ask why. And just let's reset, and let's just wait for it to do its magic, right? So now it's kind of going through every voxel that there is, and I can show you all of the voxels like so. So it's going through these voxels, and it's recording what kind of a block needs to be added to each of these voxels. And this looks pretty cool though. You can see the wire, you know, so when it chooses a correct block, the wire lights up, right? So this is pretty nice. And these are the rules according to which it's actually kind of searching, actually referencing, which is also pretty neat, I think. So by the end of it, we will have 2 lists, you know, of elements. And I just wonder how long is this gonna take? Like, it is much faster and it's not slowing down. That's the nice thing. It's not slowing down as it's going up, right? It keeps its speed, meaning that before, when we had, let's say, 10 voxels and we needed to do 10 voxels, it would do it in 1 second, right? But then if you needed to do 20 voxels, it wouldn't do it in 2 seconds, it would do it in 3, right? And if you had 100 voxels, it would do it not in 10 seconds, but rather it would do it in a minute, right? So in this case, if you have 10 voxels, it's gonna do it in 1 second. If you have 20 voxels, it's gonna do it in 2 seconds. If you have 100 voxels, it's gonna do it in 10 seconds. Meaning that you're not crashing. You're not crashing your computer, right? By doing this. You're not slowing down the definition by doing this. I feel like this is a very important step in generating a crap ton of complexity. Because if I left this running for an hour, imagine how big of a structure I can get, right? So now it's done. You can see that it's at the last voxel. It's done. And I'm just going to click that sweet bake button and we will see what's up. So we're baking it out. Oh yeah. Hell yeah. We have a structure. And you can see that it's very monotonous, I guess. I guess the word is monotonous. That's fine. That is something that we can indeed fix later on. The more important part is that this is not crashing my computer. And it would be crashing if these were not blocks, right? It's still not, I mean, my graphics card still doesn't like it, but it's definitely much better compared to what it was. Let's see if I can make it faster. Yeah, without sub-D wires, that's much faster, right? So we can see how all of these voxels make up a structure. I am going to pause a video here and I'm going to create a point cloud. It's not going to be anything, anything that I haven't told you already. I'm just going to create a point cloud that is going to kind of push the limitations of my computer, and I'm going to show you what I come up with. So just give me a second. Change of plans. This is taking way too long. So I'm going to stop it here. We're at 22,000th voxel, right? So I don't want to wait that long. I will probably kind of create something even bigger and then post it on social media, like Instagram or something like that. But for now, I think this is going to be good enough, right? So 22,000. Out of those 22,000 voxels, most of them are going to be empty voxels. So I'll need to figure out a way of how we can remove all of the boxes that are empty and kind of get rid of the calculation on that part altogether. But that's going to be a secondary optimization. For now, we just want to kind of see the structure. So I'm pausing it midway through. What else? Oh, one more thing. So just to optimize it even further, I did this portion where I, instead of creating blocks from sub-D geometry, I have extracted the control polygon of my sub-D forms, and I have applied Catmull-Clark subdivision to that control polygon. So what we end up having is a pretty close approximation with a mesh of what we had before as sub-D. I think this is a little bit better because we will be able to kind of get even more information in. And my hopes are that we will be able to create a section as well. So without any further ado, I guess we can bake out these 5,543 elements in total. Not too many, but I think it should look pretty cool as well. Either way, I mean. And that's how it looks. Let's switch it up to Arctic view, just to give it a little bit of a bazinga. Yeah, I think that is quite nice. Oh, by the way, the point cloud I created by using cellular automata script that you can find a tutorial for, of course, on my channel. Cellular automata. So we can see that there are no gaps in our structure, and the structure itself looks quite nice. Yeah, this is, I think we can work with this. This is something that has this kind of a cohesive, consistent. The word that I'm looking for is consistent. It has a consistent aesthetic to it. So the plans for these kind of structures, my plan is that I will do a live stream, and I will probably do a live stream either on Sunday or on Monday, where we are going to detail these elements even further. We will create different textures for these elements, and we will grow and populate the structure with those textures. So that the whole element, or sorry, the overall structure is not going to just be a single form, like a clay form. Also, I have like a Evangelion red. I don't remember. Oh yeah. I have this preview as well. I guess this one looks kind of nice, doesn't it? Maybe I'll end it here with this Evangelion red preview. Okay, again, the files are available for my Patreon supporters. Said that, I believe if you have followed the previous tutorials, this one, just kind of seeing which parts you need to change. I hope I've explained it well enough so that you could do it. And that's it. We will be revisiting this structure during our live stream. Okay. Thanks for watching. Later.